Hi, I'm going to show you how to analyze this circuit, which is a Sallen-Key unity gain high pass filter using only Ohm's law, KCL, KVL, the unique properties of a negative fedback opamp, and a whole bunch of algebra. So we're going to derive the transfer function h of s, which is v out over vn. The answer will be in terms of R1, R2, C1, and C2. And when we're done, the transfer function is going to look something like this. All right, so let's start. Okay, so if you look at the circuit that we have right now, just like any other circuit, the first thing we have to do is to label nodes that are not obvious or not labeled. So in this case, there are a few. So for example, there's a node here, right? So I know this node is VI, this node is VO, all right? But this node is not labeled, and seemingly this one is also not labeled. So let's look at this one first. So I'm going to label that as Vx. Okay, let me just bring Vx in. All right, so Vx. Okay, so this node is Vx. All right. Now, for this node here, well, we have to look into the property of the ideal op amp, where if it is negatively fed back, which is the case here, yeah. So the negative terminal, the inverting terminal, the output feeds back into the inverting terminal. So in this case, when you have that, you're going to have these two properties. Number one, the input impedance to the op amp can be considered infinite, which means that there'll be no current flowing into the op amp. So I1 and I2 would be 0 amps. All right. And because there are no current flowing through it, there's also no voltage drops, which means that both V1 and V2 will track each other, will have the same voltage. So if this is VO, all right, so if this is VO, then this node on the non-inverting side terminal will also be VO. So let me just put that in there, right? So this will also be VO, okay? All right, so then you have, I think all the nodes are now labeled. So that's VO, all this is VO, that's ground, that's VX, and that's VI. So next, let's label the currents. So I'm gonna define this particular current here as the one that goes through R1. All right, so I'm gonna call it IF for feedback current. So it's being fed back from the output. So it goes through R1, and then it comes through to this junction here. Then it has a split to the left and to the right. So I'm gonna call the one on the left I1, okay, and then the one on the right, I'm gonna call it I2. Now notice that the I2, I've labeled it in a way that the flow is completely bypassing the non-inverting terminal, and that's because of the assumption that we made earlier. All right, so there will be no current flowing into the non-inverting terminal. So that means whatever current goes through C2 will also completely go through R2. So I'm labeling that current as I2. All right. Okay. So now that we have all these currents labeled and nodes labeled, let's just figure out some equations that we can then use to derive the transfer function. Because remember, in the end, we need to get to an expression of V out over Vn. All right. Okay, so the first thing we can look at is, well, one of the obvious one is about IF, I1, and I2. So this is just KCL. All right. So for KCL, I can write IF is equal to I1 plus I2. All right. So that's our first equation, a KCL equation. IF equals to I1 plus I2. All right. Next, let's have a look. What else can we do? Let's see. Well, we can look at the equation for IF itself. So eventually we need to do this. So might as well figure out an equation for IF, an equation for I1, and finally an equation for I2. Let's start with IF. Well, IF flows from the node VO to node VX, and it goes through R1. So we can write Ohm's law. All right. So this is just about IF. So IF, I equals V over R. So the V is going to be VO minus Vx, all right, divided by R1, all right? So that's our first equation for IF. Okay, what else can we do? Well, we can look at the other ones, of course, like for example, I1. Well, I1 is relatively easy. It is simply a current that flows from Vx to Vi across the capacitor C1. All right, so we can write I1 is equal to Vx minus Vi divided by 1 over, remember, yeah, so it's a capacitor, so the impedance is 1 over SC1, right? Okay, so that's I1. And now we come to I2. Now, I2 has a few options here. So I2, you could talk about the I2 that flows through R2 alone, the I2 that flows through C2 alone, or the I2 that flows through both C2 and R2. Okay, so well, I'm gonna use the one that is just across C2. Of course, you can use the others as well. I mean, eventually you will end up uh, with the same answer. All right, so let's just talk about I2 going through C2. So therefore, it is a Vx, yeah, Vx to Vo, so Vx minus Vo divided by 1 over, again, it's a capacitor, so the impedance is 1 over SC2. All right, so that's basically the three equations that we have. Now, I mean, eventually we want to make an equation that has a V out and V in it. So, I mean, if you look at the equations at the moment, Vx is the only one that is still a bit of an unknown. Okay. So to figure out what Vx is, if you look, I'm gonna use this particular branch of the circuit where Vx, the current I2 that is, flows through, like I said before, flows through C2 and R2. And since there are no current going through into the non-inverting terminal, so all the current flows through here, which means that this is actually now actually a potential divider. So if I were to redraw that, just just this part alone, it will look something like this. All right, all right. So you have the VO, that's the output side here across R2. That's across R2, and then you have VX, which is from ground to the left of C2, which is here. So Vx is the whole across both components, and of course I2 flows down through both components. All right, so I'm just going to put it here. All right, so I2 flows down completely from top to bottom. So therefore, this is actually a potential divider. All right, so we can actually come up with an equation uh, that uh, you know uh, explains Vx in terms of VO, C2, and R2. Okay, let's do that. All right, so potential divider equation. All right, so we're gonna have, okay. So what do we have here? Well, we need to your typical potential divider equation. You'll say VO is equal to Vx, right? So that's the voltage across both components, multiply by uh, the component that is across VO, right? Sorry, R2, R capital R2, right? Divided by, now it's the impedance of C2, so it's going to be 1 over SC2 plus R2. Okay, so I think one more. I don't need so many. Hang on, let me get rid of all this extra bracket. Okay. All right, so that's Vx. Okay, actually I prefer, because it's going to take up the space. Sorry, let me just remove this bracket completely and just put it there. All right, so there you go. So that's my potential divider equation for VO. All right. Now, I'm just on the right side here. I'm just going to not make it into a fraction. So I'm going to multiply everything by SC2. So then on the top, you're going to have SC2, R2. And on the bottom, you're going to have 1 plus SC2. Oops, sorry. 1 plus SC2, R2. Okay. Okay, so so therefore we can write, I'm sure to rewrite this in terms of Vx equals something. So we just have to flip the thing around. So what you're going to get is a Vx is equal to VO multiplied by, so I'm going to open an initial bracket here, 1 plus SC2 R2 all divided by SC2 R2. Okay, all right. So I'm just going to put the VO to the side of it. Okay, so all right, so that's the expression we have for Vx in terms of VO and the other components. Okay. Okay, so now we have we have what we need. We just need to substitute, this IF, I1, I2 into the original KCL equation and replace all the Vx with this term here. So let's do that next. Okay, so substituting into our KCL equation. Okay, so first of all, you're going to get your IF, which is going to be this. I'm just going to copy this. Is equal to I1. I1 is just this. Oh, sorry. Oh, okay, sorry. I think I should make this a bit easier so that it becomes a flat equation. So we key SC1 multiplied by Vx minus V1, Vi, sorry. Okay, so that's I1. And then for I2, again, I'm just making it a bit simpler. So it's going to be SC2, and it's going to be Vx minus VO. All right. Okay, so that's what I'm going to use for my I1. So this is my I1. Plus I2. This is my I2. All right. Okay, so this is what I have from my original KCL, substituting these guys into the equation. All right, so next, let's substitute Vx into this unwieldy looking thing. So let's do that. So this is now substituting Vx. Into the KCL. All right, so I'm just gonna copy this whole thing here. Okay, and they're gonna copy this and replace all the Vx with that term. All right, so instead of Vx, it'll be that. Instead of this Vx, it'll be that. and instead of this Vx, it'll be this. Okay. All right. Okay, so I see this term is recurring quite a bit, and it's a bit unwieldy. So I'm gonna make it. I'm gonna apply a substitution. So if I say let a, right, let a is equal to uh, that term, this term here. All right. So if I let a equals to that term, uh, then I can rewrite the equation again. All right. So let me rewrite that equation. So then if I do that, okay, then my equation now becomes, let me just copy this here. So now, so this is now A. This is also A. This is also A. Okay. All right. Okay. So here I can clearly see it's going to be a VO and then 1 minus A. And then over here is going to be VO is going to be VO and then A minus 1. So I think it'll be useful to just quickly figure out what 1 minus A is, and therefore what uh, A minus 1 is. All right, so let's just do this. So A minus 1 would be equal to, so what's A minus 1? Well, so A is this, right? So A is that. And then minus 1. So that's therefore, so basically I'm SC2R2, I'm multiplying it across to 1. So I'm going to get, in the denominator, sorry, in the numerator, I'm going to get it a 1 plus SC2R2 minus SC2R2. Okay. All over SC2R2. Well, these two terms cancel out, SC2R2 and this SC2, because 1 minus the other. So what you're gonna left with is just 1 over SC2R2, right? Okay, so that's what you get for A minus 1. So conversely, for 1 minus A, it's just the negative of A minus 1. So therefore the answer is going to be negative 1 over SC2R2. Okay, so that's what it is. Let me just get rid of the bracket here. All right. So A minus 1 is 1 over SC2R2, and 1 minus A is negative 1 over SC2R2. All right. So then we can then, again, let me just bring this to the left. So replacing A, replacing for A. Okay, so what we're going to get is, well, this one is going to be, because there's VO in both, so it's going to become V underscore O for output, and bracket 1 minus A, right? So factorizing VO. Okay, so I'm going to get that. And then this side, well, I'm going to expand it because there's not much I can do here. So it's just going to be SC1 VOA, right? So I'm going to put VO in the front. Okay. I put VO in the front. And then there's A, right? There's A. There's A. Okay. Minus SC1 times V1, right? So that's the sorry, VI part, right? Okay, so that's this here, and this one here is this times this. All right, you got that. Okay, and then on this side, uh, you have so this one is SC2. This is VO, and in brackets A minus 1, right? So SC2 and then VO in brackets. So I'm gonna put again. Okay, I'm gonna put the VI and the VOs in the front. Makes it easy for me to see them later. So I'm gonna put VO out here. Okay, so here is just gonna be A minus 1, right? Here's gonna be A minus 1. All right. Okay, so now I can replace the A with um, the original terms that I had replaced it earlier. So now it's gonna the equation is gonna look like this. Okay. So VO. I just put it to the left. Okay, so VO. Sorry, little v. So VO, and then 1 minus A is just negative 1 over. So I'm going to copy this. So I'm going to put a negative sign in front of it. And then it's just going to be multiplied by this term. And of course, don't forget R1. Yeah, there's also R1 there. So I'm going to integrate R1 to the bottom. So it becomes R1 here. Right? Okay, so that's the left side. Now, for the right side, so VO SC1. Now A, well, A is this, so I'm just putting it back. Yeah, A is just this. So I'm just going to put this back. Okay, so that's A. Okay, make sure there's no gap here. Okay. Okay, that's this term here. All right. So now for that term, oh well, okay. I'm gonna put this VO first because I'm gonna group the two VOs together eventually. So I'm gonna say plus. So VO again. SC2. And then A minus 1. Well, A minus 1 is positive 1 over this. So multiply by, multiply by that. So multiply by that. And so that's, okay, so now this is what I have. Next thing I'm going to do, I'm going to split this into 2 because there is a, plus them. So I'm going to split this into 2. Well, before I do that, I think there are some cancellations that I can do. So for example, there's S in both. So I can cancel that S. And I can also cancel this S, right? So those two will cancel out. So on this side, I think that's the only thing you can cancel. On this side, you can cancel out S and C2. So it just becomes VO over R2, right? So let's just rewrite this again. Negative VO. So we'll still keep this as it is. Okay. But on the right side, we're going to split up these two terms. Now remember, the S has canceled out. Yeah, so what's left is just VO. So S is gone. So C1. So that's going to be okay. Then all this is over C2 over R2, right? Divided by C2 over R2. Okay. So that's the first. That's the first term. That's VO. S is gone. So VO C1 times 1 over C2 R2, right? Plus. Okay. So again, it's VO. Uh, so this time it is so when I multiply this and divide by this, the s will remain. This s will remain, but C2 and R2 would disappear. So what's left is just VO S and then C1. VO S and C1. Okay. So VO S C1. So let me just put this. Let's put this VO to the side. Okay. All right. So that's this expression being split in two. So and then there's a sorry, I think I forgot. Yes, I forgot. Sorry, I forgot the VI term here. So let me just add that VI term. All right. So let's continue. So that this one splits that one. Now we just continue on. So that's just so in this case the S and C2 cancels out. So we still have the VO, but what's left is just a 1 over R2, right? 1 divided by R2. So I get rid of this bracket. All right. And then, of course, the final, which is just VI S C1. All right. Okay. Okay. So now what we do is we multiply all the terms with this here, SC2 R1 R2, multiply across the whole thing. So then on this side it will disappear. All right. So let's do that. So times on both sides, right? So what you're gonna get? Well, you're gonna get negative VO on the left is equal to. Okay, so we're multiplying SC2 R1 R2 to this term. Well, at the bottom is C2 and R2, so that means C2 and R2 will disappear. So that means just left S R1 and then C1. So it's going to be VO S R1. Sorry, I'm gonna start with a C first. C1 and then R1. All right. Okay. So that's SC2 R1 R2 multiply with this term. You get this. Okay. All right. So next, continue plus. So again, so that multiplied by this, you're gonna get an S squared term. So again, you have a VO, but now you have an S squared term. And then you have all the passive components. C1, C2, R1, R2. All right. So that's this multiplied by this term. S squared, C1, okay. So then let's continue. So then you have this. So VO. So R2 is going to cancel out. So you're just going to get S. So S, C2, and then R1. I'm sorry, R, yeah, R1, right? Because R2 cancels out with the bottom R2 there. And finally, you have your VI. And, well, you still have to multiply. So that's S squared. So S squared, and then all the passive components. Oops, sorry. 2, R1, and R2. Okay. All right. So, okay, so now we can gather all the VOs onto one side. Okay. So collecting all the VOs together. So let's just collect all the VOs together. Collect VOs together. All right. So on the left side is going to be negative VO. Okay, negative VO. And then minus the first one. So minus. Okay, so I'm going to factorize because they all have going to have VO. So I'm going to factorize a VO out. All right. So I'm going to start with negative VO and open brackets. So the first one is going to be a 1. So that's the for this term. And then it'll be negative of this. So negative and negative is going to be positive. So it's going to be plus. All right. S C1 R1. Okay, I'm going to do something further. If you notice here, there are two VOS. Yeah, VOS. So one is C1R1, the other one is C2R1. So it's actually R1 is common. So it becomes SR1, right? So it's going to be SR1. And then in brackets, C1 plus C2. Okay. So that's these two combined, this one and this one, right? So when it goes to the other side, they both becomes negative, but then because I'm putting a negative outside of the bracket here, so they go back to becoming positive inside the bracket. And then finally, I have this S squared term. So again, plus is just S squared. And then all of this, C1, C2, R1, R2. Okay. So that is all of the VO transferred to the left. And then what's left on the right-hand side is, of course, negative VI. And then you have this term. Yeah. I'm just going to copy it. Okay. Copy that. Put it down here. All right. Okay. So now we can combine, we can actually put it in terms of VO over VS, like what we intended as a transfer function. So, all right, so therefore the transfer function, okay, denoted by H of S, is equal to simply VO of S over VI of S. Okay, I think I need to, hang on. I need to put this in brackets because otherwise, okay, divided by VI of S. All right, okay. So basically this whole term here ends up at the bottom of this term, and VI goes to the other side. All right. So that means on top is going to be this divided by all of this. Now I'm going to rearrange this so the S squared is at the front. So it's going to be, let's put it in brackets. Okay. And then plus then the S term. And then plus 1. Oh, what did I do there? Hang on. Okay. And then close this. All right. So so normally we don't leave it in this form. We usually would like to have the s squared term by itself. So which means what we can do next is we can divide this equation with the product of all the passive components. All right. So let's do that as a final line. Okay. So basically, we're dividing by this. All right. So dividing by those terms. So you're gonna get h of s. Okay, I'm gonna scroll down a little bit so that you guys can see this. Is there anything I can? Okay, I'm just gonna continue here and I'll show. I'll just make this box bigger. Okay. Okay, computer's not cooperating with me today. All right. All right, so let's continue. So h of s is equal to, so the top term will just be s squared divided by, this is the long expression. So the first one is still just simply s squared, all right, plus, now, if I were to divide this term with that term, the only thing that cancels out will be r1, right? So r1 is the only one that cancels out. So it's going to be s, and then you're going to have a c underscore 1 and c2, and all of it is divided by what's left. So so r1 cancels out, so it's going to be c1, c2, and r2, right? So c1, c2, r2, c1, oops, c underscore 1, c underscore 2, and r underscore 2. Okay. Okay. So that's the middle term, and then finally the last term will just simply be 1 over all of these values, all of these passive components. All right. So again, I need to expand this a bit so you guys can see. All right. And that's the final term. Okay. Okay, so let me just bring back what I showed you earlier. All right. So s squared, s c1 plus c2, c1, c2, r2, 1 over c1, c2, r1, r2, and then s squared at the top. All right. So I hope you guys understand how this was done. It's I'm not using anything fancy. It's just basically basic electronic laws, Ohm's law, KCL, KVL, in order to derive this expression. All right. See you in the next video. Bye.